Section: Introduction. We're diving into the fascinating world of Bayesian inference, a method of statistical reasoning that dates back to the 18th century, thanks to Thomas Bayes. Bayes' theorem, which came to light after his death in the 1760s, set the stage for using probability to make sense of data and uncertainty. Over the years, this approach has significantly influenced various fields, from physics and medicine to artificial intelligence, AI. In recent times, the blend of Bayesian methods with deep learning, known as Bayesian deep learning, BDL, has caught the eye of many. Despite its promise for making models more reliable and robust by estimating uncertainty, it hasn't become as popular as one might expect. One major hurdle is its difficulty scaling up to the large models common today. Yet, we believe BDL has a lot to offer, especially for the complex models that dominate AI. Our paper takes a closer look at why BDL hasn't taken off as expected and explores how we can overcome these obstacles. We argue that understanding and managing uncertainty is crucial, now more than ever, because of the vast and complex models we use. For instance, large language models often fail to handle unexpected inputs well, showing a clear need for better uncertainty quantification, a strength of BDL. The paper is organized into sections that discuss the importance of BDL, the challenges it faces, and potential research directions to make BDL as efficient as traditional deep learning methods. We wrap up with our thoughts on the future of BDL. Why is Bayesian deep learning important? BDL combines the principles of Bayesian inference with the power of deep learning, offering a way to deal with uncertainty more effectively. Unlike standard deep learning that gives you a single, best guess, BDL provides a range of possible outcomes and how likely each is. This is incredibly useful when dealing with limited or noisy data, or when you want to incorporate existing knowledge into your model. BDL's ability to update its understanding as new data comes in makes it a powerful tool for a wide range of applications, from healthcare and drug discovery to agriculture and autonomous driving. One of the key benefits of BDL is its approach to uncertainty quantification, UQ. UQ can make AI systems more reliable by indicating when they're unsure about their predictions, which is especially valuable in critical situations like healthcare. It can also help manage the risks of new challenges, such as the misleading outputs from language models or the vulnerabilities to adversarial attacks. In fields where data is scarce or experiments are costly, BDL's robust uncertainty estimates can guide decision-making and optimize resource use. In summary, despite the challenges, BDL has a lot to offer. By addressing its scalability issues and further exploring its potential, we can unlock new possibilities for AI applications across a broad spectrum of fields. Section Summary. The section introduces the historical roots of Bayesian inference and its evolution, emphasizing its impact on various scientific disciplines. It also highlights the emergence of Bayesian deep learning, BDL, and its potential to provide uncertainty estimates and improve model generalization and robustness, especially in the context of largely parameterized deep learning models. The significance of BDL lies in its ability to provide a full probability distribution over parameters, allowing for principled handling of uncertainty, which is particularly valuable in real-world scenarios with limited or noisy data, and in safety-critical domains. Section: Data Efficiency. We're discussing the concept of data efficiency in the context of Bayesian deep learning, BDL. Unlike many machine learning methods that need a lot of data to work well, BDL uses existing knowledge and updates what it knows as it gets new data. This means BDL can learn a lot from a small amount of data, which is really useful when it's hard or expensive to get a lot of data. The way BDL uses probabilities helps it avoid fitting too closely to the training data, which means it can make better predictions with fewer examples. It's also good at dealing with data that doesn't fit the norm, making it a great choice for fine-tuning models when you don't have a lot of data or the data you have is very spread out. BDL's ability to handle uncertainty is especially useful because it can pick the most useful data points to label. This makes the process of active learning, where the model learns from new data in a smart way, much more effective. This could be really helpful for quickly choosing the best examples to learn from in situations where you're trying to improve a model based on feedback or examples. When it comes to adapting to new and changing areas, BDL shines by updating what it knows based on new information. This means it can keep the useful stuff it's learned from past tasks while getting better at new ones. This ability to transfer knowledge is key for AI systems that need to adapt to new situations or changes over time. This is a big step up from traditional machine learning models, which don't handle new and changing data very well. In terms of understanding and choosing the right model, BDL uses a method called Bayesian model averaging, BMA, to deal with uncertainty about which model structure is best. Instead of sticking to one fixed model, BMA looks at a range of possible models. This helps make predictions more reliable by considering different model structures and parameters, leading to more trustworthy and understandable outcomes. However, there's still a need for more research to make these processes clearer, especially in scientific areas where understanding the model's decisions is crucial. Now, let's talk about the challenges BDL faces. One big issue is the computational cost. Even though BDL has a lot of advantages, methods like Gaussian processes are still preferred for really complex problems because they're less computationally intensive. Making BDL more efficient and practical for real-world applications is an important challenge that needs to be addressed. We also dive into Laplace and variational approximations, which are ways to simplify the complex math behind BDL, making it easier to work with. These methods use information from the data to create simpler models that are still very effective. They're particularly appealing because they don't add much extra computational work. However, these approximations have their limits, especially because they might not capture the full complexity of the data's underlying patterns. In summary, BDL offers a lot of promise for making machine learning more efficient and adaptable, but there are still challenges to overcome, especially in terms of computational efficiency and understanding the models it creates. Section Summary. Bayesian Deep Learning, BDL, stands out for its data efficiency, leveraging prior knowledge and updating beliefs to extract meaningful information from small datasets, preventing overfitting, and resisting the influence of outliers. BDL's adaptability to new domains allows selective retention of valuable information from previous tasks while adapting to new ones, crucial for continual or lifelong learning. Additionally, BDL's Bayesian model averaging, BMA, calibrates uncertainty over network architectures, offering a robust framework for more reliable and interpretable predictions, despite the computational cost incurred. Section: Ensembles. We're discussing a few key topics in the realm of Bayesian deep learning, BDL, starting with ensembles, moving through posterior sampling algorithms, touching on prior specification, and finally addressing scalability. Ensembles. In simple terms, creating deep ensembles involves training the same neural network multiple times with different starting points and then combining these models by averaging them. This technique is quite good at estimating what we expect to happen on average, a concept known as the posterior predictive distribution. There's been a lot of talk about how these ensembles relate to Bayesian methods, which are a more traditional statistical approach. A big question in BDL is whether we can come up with methods that are both scalable and better than deep ensembles. Some studies have shown that a method called Hamiltonian Monte Carlo often does better than ensembles but requires a lot more computing power. This becomes a problem with very large neural networks, leading researchers to look for more efficient ways to build and use these models. Posterior sampling algorithms. Within BDL, there's a group of techniques known as stochastic gradient Markov chain Monte Carlo, SGMCMC, that are popular but slow. They take a lot of time because they don't just find the most likely outcome but explore a range of possibilities, which is important for understanding uncertainty. However, these methods are still considered too slow for practical deep learning. Some newer approaches, like Stein variational gradient descent, try to balance between optimizing and sampling to speed things up, especially in Bayesian neural networks. Yet, these methods struggle with very complex problems. Some improvements have been made, like changing the step size in a cycle, but accurately capturing the full range of possibilities remains difficult. Prior specification. When we talk about priors in BDL, we're essentially discussing our assumptions before seeing any data. Interestingly, the way neural networks are built already gives us some useful assumptions. For example, using a convolutional neural network automatically assumes some level of translation invariance. However, specifying these assumptions directly on the network's parameters is hard due to the complexity of the task. Recent efforts focus on making these assumptions more about the functions the network can represent rather than the specific values of its weights, although this approach has its own challenges. Scalability. A big issue in BDL is making these methods work efficiently at a large scale. Some of the complexity in neural networks actually helps by allowing the model to explore many options quickly. Contrary to what some might think, Bayesian neural networks can be more memory efficient than traditional neural networks. Some strategies, like reusing data from the training process, can make Bayesian methods nearly as fast as non-Bayesian ones without extra computing costs. There are also hybrid models that mix neural networks with Gaussian processes, offering a good balance between speed and memory use. However, ensuring that these models are both efficient and useful, especially when resources like GPU time are limited, is a major challenge. Achieving this balance without sacrificing the model's performance or its ability to handle uncertainty is what we're all striving for in BDL. Section summary. Deep ensembling involves retraining a neural network with different initializations and averaging the resulting models to approximate the posterior predictive distribution. However, scalable Bayesian inference methods that outperform deep ensembles, such as Hamiltonian Monte Carlo, often come with significant computational overhead, especially for large and computationally expensive deep learning models. Addressing the complexity and identifiability issues arising from symmetries in the context of Bayesian deep learning can significantly impact scalability, and striking a balance between uncertainty quantification and computational cost remains a grand challenge in approximate Bayesian inference. Section. Foundation models. We're currently witnessing a significant shift in the world of deep learning, moving towards what's known as the foundation model era. Unlike before, where models had millions of parameters and focused more on vision, these new models boast billions of parameters and primarily concentrate on language. However, the exploration of Bayesian deep learning (BDL) approaches to these large language models (LLMs) is still in its infancy, both in terms of methods and applications. While current algorithms can manage models with millions of parameters, only a few studies have looked into applying Bayesian methods to LLMs. As we've discussed before, BDL offers a way to overcome some of the limitations of foundation models, especially when data is scarce. This is particularly useful in situations that involve personalized data or when trying to infer causal relationships, like estimating the effect of a treatment on an individual, where datasets are often small. BDL's ability to estimate uncertainty fits perfectly here. It also proves useful in fine-tuning these large models with limited data. So, we're at a point where foundation models present a new frontier for BDL research, especially in terms of evaluation and applications. We're curious about which applications of LLMs or transformers could benefit from Bayesian inference tools, like marginalization and priors. More broadly, we need more meaningful applications to truly show that BDL principles can be applied beyond just proof of concept. Representing uncertainty could be particularly valuable when LLMs or other large neural networks are used in scenarios they weren't specifically trained for. For instance, Bayesian methods could be explored in time series forecasting tasks using LLMs. Looking ahead, we're focusing on overcoming scalability challenges, as highlighted in our discussion on existing BDL challenges. We're exploring newer or less common Bayesian approaches to deep learning. For example, we see a need for new posterior sampling algorithms that work better with deep neural networks. These algorithms should be more efficient, reduce computational demands, and better explore high-dimensional parameter spaces. Techniques like SGMCMC with tempered posteriors, which could benefit from ideas in optimal transport theory, score-based diffusion models, and ordinary differential equation approaches, are promising. These could help in mapping between a simpler distribution, like a Gaussian, and the complex distribution of a BDL posterior or assist in MCMC proposal mechanisms. Moreover, we're considering hybrid Bayesian approaches for the future. These would capture uncertainty in critical parts of the model while using more efficient point estimation for the rest. This could involve applying Bayesian methods selectively, where it's most useful and cost-effective, and keeping a deterministic approach elsewhere. The last layer Laplace approximation is one example of such a hybrid approach. Combining deep learning methods with Gaussian processes, GPs, has been challenging due to scalability issues, but recent advancements are promising. Deep kernel learning, DKL, is one hybrid model benefiting from these advancements. The connection between BDL and deep Gaussian processes, which are GPs emerging from infinite width limits of neural networks, could provide valuable insights into BDL theory. Section summary. The shift to foundation models in deep learning emphasizes models with billions of parameters, focusing on language over vision. Bayesian deep learning, BDL, approaches to large language models, LLMs, are relatively unexplored but hold potential in scenarios with limited data availability, such as personalized data, causal inference, and small dataset fine-tuning. Ongoing research initiatives aim to address challenges in BDL, particularly focusing on scalability and the development of new posterior sampling algorithms for deep neural networks, as well as hybrid approaches that combine Bayesian methods with the efficiency of deterministic deep learning. These approaches aim to capture uncertainty in critical areas of the model while maintaining a deterministic approach for other parts, and may benefit from recent advances in scaling up Gaussian process, GP, inference. Section. Deep kernel processes and machines. We're diving into the world of deep kernel processes, DKPs, and machines, DKMs, which are advanced methods in Bayesian deep learning, BDL. DKPs are essentially deep Gaussian processes, GPs, where the focus is on treating kernels as random variables instead of focusing on the features or weights of Bayesian neural networks, BNNs. This approach helps tackle a common issue in BDL, where the outcomes can be highly unpredictable due to the different arrangements of the model's parts. Unlike other methods that struggle with this unpredictability, DKPs usually result in a simpler, single outcome. Going a step further, DKMs expand on DKPs by considering an infinite number of dimensions. This might sound like it would make learning impossible, but DKMs cleverly adjust the likelihood to still learn from the data effectively, achieving top-notch results. They give us deep insights into what it means to infer in function space and how it connects to learning representations of data. Essentially, DKMs learn a series of function spaces, layer by layer, that focus on the most important features for making predictions. In another area, we've seen unexpected success with semi-supervised learning in deep learning, despite it not fitting neatly into traditional Bayesian models. This success, however, seems to depend heavily on the quality of the data. If the data isn't carefully selected, the benefits of semi-supervised learning might not hold up. Similarly, the cold posterior effect, where models perform better when the outcomes are artificially made less likely, suggests that these models might be too cautious in their predictions. Self-supervised learning offers an alternative, focusing on learning from the data itself without needing labels, though it also faces challenges in fitting into a Bayesian framework. The evolution of deep learning is also closely linked to advancements in computing, like the use of GPUs and the exploration of mixed precision computing. Mixed precision introduces a bit of uncertainty into calculations, which Bayesian methods can handle well, ensuring that we make the most out of our computational resources. There's also a push for creating hardware specifically designed for BDL, which could greatly improve how we do inference in these models. To make BDL models more manageable, we're looking into ways to compress them. This includes using certain priors to reduce the size of BNNs or to compress the weights of the networks more efficiently. These strategies not only save on computational resources but also offer a balance between the cost of compression and the quality of predictions. In summary, the field of Bayesian deep learning is evolving, with DKPs and DKMs offering new ways to approach deep learning models, semi-supervised and self-supervised learning challenging traditional Bayesian methods, and advancements in computing and compression strategies pushing the boundaries of what's possible. Section Summary. Deep kernel processes, DKPs, are deep Gaussian processes where the kernels, rather than the features, are treated as random variables, resolving the issue of highly multimodal posteriors in Bayesian deep learning. Deep kernel machines, DKMs, take the infinite width limit of DKPs, retaining representation learning and offering insights into inference in function space. Additionally, semi-supervised learning's success is attributed to data curation, while self-supervised learning uses objectives like mutual information between latent representations to learn Bayesian priors. Furthermore, mixed precision in deep learning introduces uncertainty into computations, which Bayesian methods can effectively propagate, and compression strategies such as sparsity-inducing priors and variational Bayesian quantization are explored to decrease the computational cost of Bayesian deep learning models. Section: Other future directions. We're exploring several exciting future directions in the field of Bayesian deep learning, BDL, and how it can be applied to enhance various learning paradigms and methodologies. Here's a breakdown of these directions. 1. Bayesian transfer and continual learning. Transfer learning is becoming a key technique for deploying deep learning models effectively. Unlike traditional methods that simply transfer a starting point for model training, BDL allows us to use knowledge from previous tasks to better shape and locate the best solutions for new tasks. This approach is particularly useful when dealing with data that changes over time, as it can update its knowledge base to integrate new information smoothly, whether the data changes gradually or suddenly. 2. Probabilistic numerics. This area treats numerical algorithms as if they were making decisions based on Bayesian principles. Since deep learning relies heavily on optimization and linear algebra, applying a Bayesian perspective could make these processes more efficient and insightful. For example, in situations where managing data loading is crucial due to the size of the models, probabilistic numerics could help prioritize which data to process by evaluating its impact on the overall learning. 3. Singular learning theory, SLT. SLT examines the relationship between Bayesian losses and the loss functions used in neural networks through the lens of non-equilibrium statistical mechanics. This exploration could bridge the gap between Bayesian methods and traditional neural network training, offering new insights into how we understand and implement learning algorithms. 4. Conformal prediction. As an alternative for uncertainty quantification, UQ, conformal prediction provides a way to generate well-calibrated uncertainty estimates. There's growing interest in combining the strengths of Bayesian reasoning with conformal prediction to enhance the reliability of UQ in deep learning models. 5. LLMs as distributions. Large language models, LLMs, can be viewed as distributions within complex programs, raising interesting questions about how to perform joint inference, marginalize over latent variables, and utilize computational statistics for reasoning with LLMs. This perspective opens up possibilities for innovative interactions between small and large LLMs to improve inference processes. 6. Metamodels. Inspired by the success of language models, there's speculation about developing a Bayesian metamodel that could be fine-tuned for multiple tasks, similar to how language models are adapted. This approach could significantly advance the field of amortized inference. 7. Sequential decision benchmarks. To better understand the capabilities of BDL, especially in terms of predictive uncertainty, there's a push towards focusing on sequential learning and decision-making problems. These include experimental design and active learning, which can provide deeper insights into a model's generalization ability and its performance under uncertainty. In our final remarks, we've highlighted that despite the ethical, privacy, and safety challenges facing modern deep learning, BDL offers a promising path forward. By building on principles that have stood the test of time, BDL can address many of these challenges, paving the way for AI systems that are more reliable, safe, and trustworthy. We're grateful for the support from various institutions and funding bodies that have contributed to our work, including the Eric and Wendy Schmidt Center at the Broad Institute of MIT and Harvard, the DFG Cluster of Excellence, Machine Learning, New Perspectives for Science, the German Federal Ministry of Education and Research, the Ministry of Science, Research and Arts of the State of Baden-Württemberg, the National Science Foundation, the Department of Energy, Office of Science, and gifts from Disney and Qualcomm.